Alright, now we're going to go on to the Rayleigh-Ritz method. Now, okay, how should I do this? Well, okay, Rayleigh-Ritz method. It's pretty easy. Okay, this is the main principle of the Rayleigh-Ritz method. To show you this, let me give a little example first. Let's say we have a beam like this, and on one side there is a complete support, and on the other side we have a roller. Okay, and we have some load distributed on it. It'll be a uniform load, and this uniform load is just gonna, we'll say it's Q naught. Okay, we'll call this A, we'll call this B, and let's say we're interested in finding the deflection at point C, which lies in the middle of the two. Okay, so that's the question. What is delta C? Okay, so this is what the Rayleigh-Ritz method is. First and foremost, it's an approximate solution. Approximate solution. It's not going to give you an exact solution like the other methods would. Like the unit load method would give you an exact solution to what the deflection is. But the Rayleigh-Ritz method would only give you an approximate solution. And why is it only approximate? Well, from the method itself. And this is the method. We create a function for the deflection. So when this thing deflects, it has a load on it, it's going to deflect something like this, right? It's going to deflect something like that. It's going to be kind of parabolic. And what we do in this Rayleigh-Ritz method is we approximate the form of deflection. Okay? And what does that mean? Well, since this thing is going to be parabolic, we can approximate the form of the deflection. Let's call the deflection delta as a function of x. We can approximate it as some kind of, well, I don't know, c0 plus c1 times x plus c2 times x squared. You see, we're approximating this function, and we have three unknown constants, c0, c1, and c2. Correct? Now, what is the principle of the Rayleigh-Ritz method? Well, the principle is this. It's stated exactly, it says that, stated exactly, it says that the function, the correct approximation, call it delta star, is a function that minimizes the total potential energy. Okay, and I worded this very, very specifically. So the correct approximation of the deflection is delta star, and it is a function that minimizes the total potential energy. Okay, and what is this total potential energy? And in the literature, we usually write it as pi. Pi for total potential energy. And in fact, total potential energy is actually going to be equal to strain energy, U, strain energy minus work done on the system. Okay, this is very important. So total potential energy is equal to strain energy minus work done on the system. And the correct deflection, the correct approximation to the deflection is going to be a function delta star that minimizes this total potential energy. Okay? So now it's becoming a little more clear what we have to do. We have to find the deflection, first of all. We have to find these constants, C0 to C2. We have to find the strain energy, and then we have to find the work done. And then once we have that, we can find the minimum by taking the simple derivative. Okay? So first things first, how do we find these constants? And the way we find these constants is by utilizing boundary conditions. Okay? Now, boundary conditions come in the form of the problem at hand. So in this example problem, we see we have supports at A and B. And what this means is that we can't have any deflection at A. So the deflection at A is equal to the deflection at B, and it's equal to 0, correct? And what this means is that we can immediately plug this into our form for delta of x. So delta of 0 is going to be at A. This is going to be equal to delta A, and this is going to be equal to 0. So when we plug in 0 for x, we just get C0 equals 0. That's 1. That's 1. Next, we have delta at B. And delta at B is all the way at, delta at B is all the way at L, right? Because this is the starting point of our origin. This is our origin right here. So delta B is all the way at X. So this is going to be delta evaluated at L. And then once we substitute it in, we get C0 plus C1 times L plus C2 times L squared, correct? And then C0 obviously we know is 0, so now we're just left with C1 times L plus C2 times L squared, and this is equal to 0. So immediately we see that if we cancel out an L, because we can just divide, we see that C1 is equal to negative C2 times L. That's another. That's another. And unfortunately, that's all we have for now. That's all we have for now. And you know you've done a good job at this process when you're just left with one constant at the end. Okay, this is important. You should only be left with one unknown. All right? And how do I know we only have one unknown? Well, let's rewrite our delta function, our deflection. The deflection at x is equal to C0, which is 0, plus C1 times x. But C1 is just this. So negative C2L times x plus C2 times x squared. One unknown, like I said, right? And we'll come back to this later. Next, what we have to do is find the strain energy. How do we find the strain energy? Well, there's a formula for it. Strain energy is defined to be EI over 2 times the integral from 0 to L of what? Well, this is going to be the second derivative of our deflection. Okay, second derivative squared. Okay, it's going to be the second derivative squared, and we're integrating that over dx. So EI over 2 integral from 0 to L of the second derivative of our deflection squared. So let me scroll up over here. This is our deflection. What is the second derivative? Well, the first derivative is just going to be negative C2L plus 2C2X, correct? And then the second derivative is going to be, well, this is a constant, so it's just going to be 2C2. Okay, fair enough. So I can plug this in here. It's going to be EI over 2 integral from 0 to L. And now this guy squared, so 4C2 squared dx. Okay, very simple integral. This just gives 2EI C2 squared times L. Because this guy gets pulled out, and then we're just left with L. Right? Did I do everything correctly? Yes, I did. Okay, so this is our strain energy. That was easy. Next thing we have to do is find the work done on the system. And if you remember from the very first video, work is nothing more than force times distance. But in this case, if we scroll back up here, we have a distributed load. So we're going to have to integrate over this whole distance. Okay? So the work is nothing more. Okay, sorry, I had to take a little bit of a break. But the work, where were we? Oh yeah, we're finding the work. Okay, so we're finding the work. We're gonna have to. We have a distributed load, so we're gonna have to integrate this load over the distance. Now, what we have to do actually is be careful a bit here, because this work is the work due to deflection, due to this distributed load. So what distance are we actually integrating over? Are we integrating from 0 to L? Are we just integrating over the x-axis? No, we are not. We're actually integrating over the deflection. Okay? Because think about it like this. the work you need to move a car from point A to point B. It's actually the distance the car moves, right? And the analogy here is the distance that this structure deforms. So it's actually going to be, the work is going to be equal to the integral of the load. Of course, this is the force, but the distance will actually be the deflection. Okay, force times distance. The force applied to the structure multiplied by the distance that the structure deforms. Okay, and of course from 0 to L. And since Q is constant here, it's amazing. It's going to be an easy integral. So now we just have to plug in delta, and I can bring out the Q, so it's going to be integral from 0 to L. And what was delta again? Delta was this guy, negative C2Lx, negative C2Lx, plus 2C2 plus 2C2x, plus C2 times x squared. Okay, so it's always the load times the deformation. And once we integrate this, we get Q times negative C2L times L squared over 2, which is the integral of x, plus C2 times L cubed over 3. And then if we make this a little simpler, we can factor out a C2Q, right? We can factor out a C2Q L squared, and we're just left with L over 3 minus L over 2, right? I think I did that correctly. Yeah. Okay, so this is just... Actually, we can factor out another L, but okay, whatever. L over 3 minus L over 2 is going to be 2L over 6 minus 3L over 6 is going to be negative L over 6. So it's going to be negative C2 QL cubed over 6. That's our work. That's the work done by the load. So we have all the pieces of the puzzle here. Our total potential energy, right, total potential energy from the beginning was equal to strain energy, right here, 2EI C2 squared L minus the work, so plus C2 QL cubed over 6, correct? Okay, so we're almost done here. We found the potential energy. But now remember, the Rayleigh-Ritz method is all about finding the delta that minimizes the total potential energy, right? Minimizing the total potential energy. So we're actually taking the derivative. Let me go back to black here. We're taking the derivative of the potential energy with respect to delta. But not really with respect to delta, because delta is not explicitly in here. But what is the variable in here that we don't know? C2. So we're finding the derivative with respect to C2. And what that's going to give us is QL cubed over 6. This guy is done. Plus 2, it's going to be 4, plus 4EI L C2. Okay? And this is equal to 0 because we are finding the minimum. And when we find the minimum, we take the derivative, and of course we set it equal to 0. And as a result, we get C2, which is what we wanted. So C2 is nothing more than negative QL cubed, over 24EIL, right? I move this over, and I divide it, and then you see the L's cancel, so negative QL squared over 24EI. Awesome, that's C2. So now let's go all the way back. Let's go all the way back into our delta function, into our elongation. And do you remember what it was? It was right here, negative C2Lx plus C2x squared. So C2, negative C2Lx plus C2x squared. And let's just plug it in. There we go. And then we have x squared minus Lx. Okay, so the whole question is asking for what is the deflection at C? what is the deflection at C? And C occurs at L over 2, correct? So what we're going to do is simply plug in delta of L over 2, which is the same as delta C. And what this gives us is negative QL squared over 24 EI times L over 2 squared is going to be L squared over 4 minus L squared over 2. And just a little bit more, this is going to be L squared over 2 is 2L squared over 4. So L squared over 4 minus 2L squared over 4 is negative L squared over 4. So this is going to give us QL to the 4th over 96 EI. Okay? And that's our answer, ladies and gentlemen.